We're counting down the 10 trains with the most remarkable safety records on rails worldwide. From cutting-edge technology to century-old engineering wisdom, these machines have cracked the code on staying upright when physics says otherwise. What separates a legendary safety record from a statistical nightmare? Every day, millions of passengers place their trust in steel wheels running on steel rails. It's a relationship that seems simple until you realize how many things can go catastrophically wrong. Yet some trains have built reputations that make nervous travelers breathe easier and engineers nod with respect. If you want to see more videos about old trains that outlasted everything modern, make sure to subscribe so you never miss another video. We're exploring 10 remarkable trains that have earned their place in safety history not through marketing or hype, but through decades of operational data, thoughtful engineering, and lessons learned from when things went right. These aren't just machines. They're testaments to what happens when design philosophy meets real-world discipline. From remote mountain passes to crowded urban corridors, each train on this list has proven itself where it matters most, in the daily grind of moving people and goods without drama. Let's discover what makes these iron horses so trustworthy, starting at number 10. High in the Swiss Alps, where grades reach 11% and curves twist through ancient rock, one train has been defying mountain physics since 1930. The Glacier Express doesn't just survive the journey between Zermatt and St. Moritz. It makes the 8-hour route look routine. The secret starts beneath the carriages. Rack and pinion systems bite into specialized track sections, creating a mechanical bond that pure friction alone could never achieve. When gravity pulls downward on steep descents, these teeth keep the train locked to its path with mathematical precision. But technology alone doesn't tell the whole story. The Glacier Express operates on the Ray-Tian Railway Network, where track maintenance follows protocols stricter than most surgical theaters. Every millimeter of rail gets inspected with laser precision, every ballast stone placed with consideration for drainage and stability. In over 9 decades of operation, carrying more than 300,000 passengers annually through terrain that would terrify most engineers, the Glacier Express has maintained an operational safety record that stands at 0.003 incidents per million passenger kilometers. For context, that's roughly 3 times better than the European railway average for mountain operations. The trains crawl at a maximum speed of 24 miles per hour, earning the tongue-in-cheek title of world's slowest express train. But that deliberate pace is engineering wisdom, not limitation. At these speeds, the massive windows become observation platforms while the train's mass and low center of gravity work together to keep it planted through 291 bridges and 91 tunnels. Passengers sipping wine in the panoramic cars rarely consider the physics beneath them. That's exactly how good engineering should feel, invisible until you stop to appreciate it. Next, we cross an ocean to discover how Japanese precision engineering turned speed into safety. Beneath Tokyo's relentless urban rhythm, the Marunouchi line has been threading through the city's circulatory system since 1954. This isn't about speed or glamour, it's about moving 1.2 million people daily through 28 stations without a single passenger fatality from derailment in its operational history. The statistics alone demand attention: 0 derailments resulting in passenger injury across 70 years and counting. In a system where trains arrive with 30-second intervals during rush hour, that record borders on the miraculous. The answer lies in layers of redundancy that would make a spacecraft engineer envious. Automatic train control systems monitor every aspect of operation, adjusting speed in real time based on track conditions, train spacing, and even weather data fed from surface sensors. Human operators don't fight the system. They work within its envelope, knowing the computers will intervene before physics does. Track geometry gets measured weekly, not monthly. The acceptable deviation for rail alignment sits at just 2 millimeters, a tolerance that turns maintenance crews into artists. Platform screen doors, now common worldwide, were pioneered here in 2000, eliminating the risk of passengers interfering with train operations. But perhaps the most crucial element is cultural. Tokyo Metro employs rail whisperers, veteran workers whose sole job is walking the tunnels during off hours, feeling for vibrations, listening for sounds that instruments might miss. They catch problems before they become data points. The Marunouchi line proves that safety culture isn't just about technology. It's about creating systems where human expertise and machine precision amplify each other. Our next entry takes us to where freight meets physics on the longest continuous rail line on Earth. Spanning 5,772 miles from Moscow to Vladivostok, the Trans-Siberian Railway isn't just long. It's a masterclass in adapting to extreme conditions that would cripple lesser systems. Modern freight services on this route have achieved something remarkable, maintaining a derailment rate of just 0.1 per million train kilometers, despite operating through temperature swings of 120 degrees between seasons. The trains themselves are engineered for abuse. Heavy-duty bogies with three-piece trucks absorb lateral forces that would topple conventional designs. The suspension systems use nested springs and hydraulic dampers that treat rough track like a luxury sedan treats potholes. Russian engineers learned hard lessons from decades of harsh winters. Track expansion joints now incorporate memory metal alloys that adapt to temperature changes. Rail welding techniques create continuous ribbons of steel that eliminate the clickety-clack vulnerable points where derailments often start. Freight cars carry distributed braking systems, a technology borrowed from Western railways but adapted for the unique challenges of Siberian operations. When a 100-car freight train stretches over a mile long, stopping evenly without accordion effects becomes critical. Electronic brake distribution ensures that every car receives the exact braking force needed for its load and position. The route crosses 16 rivers, including the mighty Amur, and threads through mountain passes where grades test the limits of steel-on-steel adhesion. Yet cargo arrives on schedule with monotonous reliability, a testament to engineering that treats nature as a design parameter, not an obstacle to overcome. Next, we travel to a network where punctuality and safety have become national obsessions. Switzerland doesn't just run trains, it orchestrates them with the precision of a master watchmaker. The regional services operating across the Swiss Federal Railways network post an enviable statistic: 0.08 derailments per million train kilometers, making it one of the safest railway operations on the planet. This isn't coincidental. Swiss rail infrastructure treats every component as part of an integrated system. Track curves receive continuous monitoring through embedded fiber optic sensors that detect micro movements invisible to the human eye. If a curve shifts by even 5 millimeters, automated systems flag it for immediate inspection. The trains themselves benefit from decades of iterative improvement. Modern Swiss regional trains use active suspension systems that adjust damping in real time, reading track conditions 1,000 times per second. Banking through curves becomes a choreographed dance between wheels and rails, with the suspension system anticipating every movement. Driver training extends beyond technical competence into something closer to philosophy. Swiss engineers call it reading the railway, a skill where operators learn to sense problems through subtle changes in sound, vibration, or handling characteristics. This human element catches issues that sensors miss, creating a safety net with redundancy built from flesh and steel. Weather monitoring has evolved into predictive science. Algorithms analyze temperature, humidity, and historical data to forecast when track conditions might become marginal. Trains automatically reduce speed during these windows, trading minutes for certainty. The Swiss approach proves that safety isn't just about preventing the worst. It's about creating systems so refined that near misses never occur in the first place. Our countdown continues with a high-speed marvel that rewrote the rules of rail travel. When the Shinkansen N700S began service in 2020, it inherited a legacy that borders on the sacred. The entire Shinkansen network has operated since 1964 without a single passenger fatality from derailment or collision. The N700S doesn't just maintain that record. It pushes the boundaries of what's possible at 200 miles per hour. The train's design philosophy centers on something engineers call fail-safe redundancy. Every critical system has backups, and those backups have monitoring systems, and those monitors have override protocols. It's Russian nesting dolls of safety engineering. Seismic sensors embedded throughout Japan's rail network communicate with every Shinkansen train in real time. When earthquakes strike, and in Japan they always do, trains receive warnings before the ground even begins to shake. Automatic braking engages, bringing 700 tons of train to a controlled stop in seconds that feel eternal to passengers but represent the cutting edge of safety engineering. The N700S introduces lithium-ion battery backup systems that power critical controls even if external power fails. During the 2024 Noto Peninsula earthquake, several N700S trains executed perfect emergency stops in complete darkness, their batteries keeping brake systems, communications, and passenger information displays operational. Aerodynamic stability isn't just about efficiency. The N700S nose design reduces lateral wind forces by 12% compared to previous generations, crucial when typhoons sweep across Japan's coastal lines. Crosswind sensors trigger automatic speed reductions before wind forces can challenge the train's stability. The result? In 4 years of operation covering millions of passenger kilometers, the N700S maintains a perfect safety record while carrying capacity crowds through one of the world's most challenging railway environments. Next, we explore how German engineering turned reliability into an art form. The Intercity Express 3, Germany's high-speed flagship, operates across one of Europe's most demanding rail networks. Since entering service in 1999, the ICE-3 has compiled a safety record that makes statisticians check their calculations. 0.04 derailments per million train kilometers, despite operating at speeds up to 205 miles per hour through varying terrain and weather conditions. The ICE-3's distributed traction system spreads motors throughout the train rather than concentrating them in locomotive units. This configuration creates a lower center of gravity and distributes weight more evenly across the track. Physics becomes the first line of defense, with the train's mass profile naturally resisting the lateral forces that cause derailments. German railways pioneered predictive track maintenance using AI systems that analyze vibration data from passing trains. The ICE-3 serves as a rolling diagnostic tool, its suspension system feeding information about track conditions too. Central computers that can predict maintenance needs weeks before problems become visible. Wheel profile management reaches obsessive levels. ICE. 3 wheels undergo reprofiling every 50,000 miles, maintaining the precise geometry that keeps steel wheels following steel rails with microscopic accuracy. This attention to the wheel-rail interface prevents the hunting oscillations that precede many high-speed derailments. Cab signaling and automatic train protection systems work in concert, creating a safety envelope that's nearly impossible for human error to breach. If an operator misses a signal or exceeds speed limits, the train intervenes without drama or fanfare. The ICE-3's legacy isn't just about numbers, it's about demonstrating that high-speed rail can achieve airline-level safety while remaining accessible to millions of daily commuters. Our next entry proves that freight operations can match passenger services for safety excellence. In North American freight operations, where profit margins depend on moving heavy loads across vast distances, the BNSF Railway's fleet of ES-44AC locomotives has established a benchmark that rivals passenger services. These workhorses maintain a derailment rate of 0.09 per million train miles, exceptional for freight operations where trains can weigh 15,000 tons. The ES-44AC's design reflects lessons from millions of miles under harsh conditions. 6-motor traction, with each axle powered independently, allows the locomotive to distribute tractive effort precisely across varying track conditions. Wheel slip detection systems respond in milliseconds, preventing the wheel spinning that can lead to derailments on grades or curves. BNSF invested heavily in track infrastructure, but the locomotives themselves contribute through distributed power systems. Instead of one massive locomotive pulling from the front, ES-44AC units position throughout the train, creating balanced forces that prevent the accordion effects and string lining that cause freight derailments. Predictive maintenance using onboard diagnostics means locomotives rarely experience unexpected failures. The ES-44AC reports over 3,000 data points continuously, from bearing temperatures to brake pressure anomalies. Maintenance crews receive alerts before components reach failure thresholds, keeping trains operational and safe. The success of these locomotives stems from treating safety as an operational asset rather than regulatory burden. When derailments cause delays and damage, prevention becomes profitable. The ES-44AC proves that economic incentives and safety goals can align perfectly. As we approach the top 3, the stakes get higher and the engineering gets more sophisticated. Beneath Paris streets, Line 14 represents the future of urban rail safety. Fully automated since its 1998 opening, this driverless system has achieved something unprecedented. Zero derailments and zero passenger injuries from train operations across 26 years, despite carrying 550,000 passengers daily. The secret is eliminating human error while retaining human oversight. Trains operate autonomously, controlled by computers that never get distracted, tired, or overconfident. But central controllers monitor every aspect, ready to intervene if the unexpected occurs. Platform screen doors make accidents impossible. Passengers can't fall, jump, or be pushed onto tracks. This single innovation eliminates an entire category of incidents while allowing trains to operate at 2-minute intervals safely. The rolling stock itself features articulated designs that distribute weight across multiple bogies, creating inherent stability. Suspension systems use active damping that adjusts to passenger load in real time, maintaining optimal ride characteristics whether the train is empty or packed. Track monitoring reaches paranoid levels. Fiber optic sensors embedded in the track bed detect temperature changes, vibrations, and structural shifts with sub-millimeter precision. Automated inspection trains run nightly, using laser scanning and ultrasonic testing to find flaws invisible to conventional inspection. Line 14's success has influenced metro designs worldwide, proving that automation doesn't reduce safety. It amplifies it by creating systems where consistency and vigilance never waver. Now, we reach the top two, where safety records transcend statistics to become cultural phenomena. The Copenhagen Metro operates with a safety record that seems almost too perfect to be real. Zero derailments, zero collisions, zero passenger fatalities in 24 years of 24/7 automated operations. This isn't luck. It's the result of Danish engineering philosophy applied to urban transportation. Built from the ground up as an automated system, the Copenhagen Metro never had to retrofit safety onto existing infrastructure. Every curve radius, grade transition, and station approach was optimized for automated operations from the first shovel of dirt. The trains use Bombardier's City Flow 650 automatic train control, a system so refined that it makes human operation seem reckless by comparison. Trains communicate with central computers constantly, reporting position, speed, door status, and system health with redundant communication channels, ensuring data never gets lost. What sets Copenhagen apart is predictive risk management. The Metro Authority doesn't just respond to problems, they model potential failure scenarios using simulation software, testing responses to everything from power failures to earthquake scenarios. These simulations inform maintenance schedules, training protocols, and system updates. Track geometry gets measured continuously using onboard laser systems, building a dynamic digital twin of the entire network. Deviations trigger alerts before they become measurable by traditional inspection methods. The Metro's success demonstrates that purpose-built systems, free from legacy constraints, can achieve safety levels that retrofit projects struggle to match. But even Copenhagen takes second place to our final entry, a system whose safety record has become the gold standard worldwide. The Mass Transit Railway of Hong Kong sits atop this list with a safety record that defies belief. In over 45 years of operations, moving 1.8 billion passengers annually across 246 miles of track, the MTR has achieved the unthinkable: 0.13 injuries per million passenger journeys, with derailments so rare they become international news when they occur once per decade. This isn't about one innovation or lucky circumstances. It's about creating a safety culture so thorough that excellence becomes automatic. The MTR treats tracks like living systems. Inspection teams walk every mile of track nightly, checking for defects with handheld ultrasonic equipment that finds cracks before they propagate. Major inspection cycles happen weekly, using automated track recording cars that measure 50 different parameters simultaneously. Rolling stock undergoes maintenance on strict 4-day cycles. Trains never run longer than their planned service intervals period. This discipline costs money, but saves. lives by catching wear patterns before they become failures. Driver training extends to 18 months, longer than many pilot programs, but MTR operations are increasingly automated with drivers functioning as system supervisors rather than controllers. The trains themselves can operate autonomously, with humans present to handle the unexpected. Platform screen doors, pioneered widely here, eliminate platform edge accidents entirely. Over 90% of MTR platforms feature full-height barriers, creating a physical separation between passengers and trains until doors align perfectly. The signaling system uses moving block train control, allowing trains to operate at 2-minute headways while maintaining safety margins that would satisfy aerospace engineers. Trains know where every other train is, constantly recalculating safe braking distances and adjusting speed automatically. But technology alone doesn't explain the MTR's record. The organization treats every near miss as a learning opportunity. Incident reports get distributed system-wide, analyzed in training sessions, and incorporated into updated procedures. This learning culture turns mistakes into wisdom. Hong Kong's geography forced the MTR to solve problems other systems avoid. Steep grades, tight curves, and limited space required innovations in suspension, braking, and control systems. These challenges became opportunities for engineering excellence. The financial model matters too. The MTR Corporation operates profitably, using property development revenue to fund world-class maintenance and upgrades. Safety becomes sustainable because the business model supports it. Passengers rarely notice the countless systems protecting them. The MTR delivers them to destinations on time, every time, with such consistency that safety becomes invisible. That's the ultimate achievement, making extraordinary safety feel ordinary.